Welcome back. We're finishing off chapter 3 in this video, talking about ordering and exponents in the whole numbers. To start off talking about ordering, we're first going to talk about the relationship less than. And so if I take two whole numbers, A and B, so that's what this notation means, remember, A and B are elements of the set of whole numbers, then A is less than B. Remember, this means if and only if there is a number n in W, so another whole number that's not 0, so that A plus that whole number is equal to B. So I'll write down, this is if and only if, and this is there exists. Okay, so A is less than B if there's some other number, other whole number that I add to A in order to get to B, is how we want to think about this definition. And the symbol that we use to say that A is less than B is this little caret. And of course, the one way of thinking about which number is bigger and which is smaller is that the alligator or the Pac-Man or whatever you like to think of it as eats the larger number. Okay, so this relationship has a few different properties that we're going to discuss. And here we're not really talking about an operation because less than isn't something that we do to the whole numbers. It's just some property that two numbers already have, I guess. So the first property that this relation has is one that we haven't discussed yet. It's transitive. So what it means for this relation to be transitive is that if I take three whole numbers, if A is less than B and B is less than C, then I know that A has to be less than C as well. So we can visually see this looking at this number line here. Here I have A to the left of B because A is less than B, and then B to the left of C because B is less than C. And then last but not, what this definition means is that if I add a little bit to A, there's some whole number that I add to A to get B, so I might add n to get B, and there's some little whole number that I add to B in order to get C, right? That's what this definition of less than means. It means there's some number, A being less than B means there's some number I add to A to get to B. B being less than C means there's some number I add to B to get to C. We'll call it M in this case. And so in order for A to be less than C, there's some number I need to add to A in order to get C, some whole number. And of course, that whole number is going to be M plus N, right? So I'm going to add M plus N to A in order to get to C. Okay, so that's kind of an intuitive justification as to why this transitivity property holds for less than. Now, we know of other relations that are transitive as well. For example, equality is transitive. If A is equal to B and B is equal to C, that means that A has to also be equal to C. And there are examples of transitivity in our everyday life, like the relationship of being a sibling. So if you are my sibling and there's another person that is your sibling, that person is my sibling as well. That relationship is transitive. However, something like the mother of is not transitive. So I might I'm a mother of my child and they might be even a mother of their own child, but I am not the mother of that third child, I'm the grandmother. So that's another example of something that is not transitive. Okay, so some other properties that the inequality has if we say that A is less than B, then if I add a little bit to A and I add the same little bit to B, then A plus C is, is also less than B plus C. And we can understand why this is by looking at this justification on, or this definition or characterization of less than on the right here. So why is this true? So if we want to talk about explaining why like something that's an if-then statement is true, I want to start off by assuming that this is true. So assume or supposing that A is less than B. And what I want to show is that A plus C is less than B plus C. And this is for A, B, and C being whole numbers. Okay, so let's assume this is true. So this means there is some whole number n not equal to 0, so that A plus n is equal to B. That's just how our characterization on the right works, right? It's just literally what it says. So now let's take this equality and let's add C to both sides. So this means that A plus N plus C is equal to B plus C. And of course, addition here is commutative, which means that I can change the order of these two terms. So this means that A plus C plus N is equal to B plus C. And now A plus C and B plus C satisfy the same relationship that A and B had up here. And what that means is A plus C is less than B plus C. By this exact definition of less than. Okay, because what it means for A plus C to be less than B plus C is that if I add a little bit to A plus C, I get B plus C. Okay, the last property that we're going to talk about with regards to ordering, we're going to, if we assume that A is less than B again, and we also assume that C is non-zero, then if I multiply by C on both sides, A times C is less than B times C. Now this one, of course, only holds if C is a whole number. If we're talking about negative numbers, the inequality might switch, but we'll touch on that later on in the course. Okay, so we start off, and I encourage you to maybe try pausing the video here and writing out a justification for property number 3 here on your own first. But here I would start by assuming what is on the left here. So after the if, but before the then. So I'm going to assume or suppose that A is less than C, or sorry, A is less than B, and that C is non-zero. So again, this means there is some whole number, some non-zero whole number, so that A plus N is equal to B. That's again, just the exact same characterization we had on the right here. Okay, so last time what we wanted was we started with this same characterization, but what we wanted was to look at B plus C, so we added C to both sides. But here we want to look at B times C, right? That's what we're aiming for, is some relationship with B times C, not B plus C. So let's multiply by C on both sides. So this means that A plus N times C is equal to B times C, multiplying on both sides. And On the left here, I can go ahead and distribute this C to both terms. So this looks like AC plus NC is equal to BC. So now this is the constant that I add to AC to get to BC. And it's definitely a whole number because it's multiplying a whole number n times a whole number C. And it's also non-zero since n is not zero and C we said is not zero. So that means that AC has to be less than BC since NC is a whole number and NC is not equal to zero. Great, and that's exactly what we wanted, what our goal was that we wanted to achieve. Okay, so these are the three properties that we have for our inequality here. So if I have an inequality between two whole numbers and I add a little bit to both sides, the inequality still holds. Same thing happens if I multiply by both sides. So one thing, maybe one question to think about is what happens if I did not assume that C was non-zero here? Would this statement still be true? So if I eliminated this extra assumption, if I just assume that A was less than B, would I still be able to show that AC is less than BC? Or what happens? So maybe think about that for a second or pause and think. And in fact, this would no longer hold because if C were zero, this would mean the left-hand side is zero and the right-hand side was zero. And zero isn't less than zero, it's equal to zero, or it's maybe less than or equal to zero, but we're not including the equality here on this side. Okay. So to finish off this chapter 3, we're going to talk about exponents as the last kind of operation. And so if I have two whole numbers, A and M, but I again assume that the M is non-zero, then A to the power M is really just A multiplied by itself M times. So there are, again, of course, a few properties we're going to discuss with regards to whole numbers. So, given this definition that we just wrote down of exponents, discuss with a peer why each of the following might be true. So maybe I'll write out why I think the first one would be true and using this definition. And maybe we'll pause then and have you think about similar justification for the other three. So here, I would think about what the definition of A to the M and A to the N means. This means A times A times A M times. And then, of course, this means A times A times A N times. Now, since everything is being multiplied, these parentheses don't actually really matter. And so this is the same as A times A times A, this M times, and then I'm going to multiply by A another N times. So altogether, I have M plus N times that I'm multiplying A. So this is the same as A to the M plus N. And that's exactly what this first property says, that if if I multiply two exponents with the same base, I can just go ahead and add the exponents here. So this is some sort of justification for that first property here. So maybe take a moment and pause and see if you can, or pause the video and see if you can justify number 2 here. And maybe even if you have a stab at that, think about 3 and 4. Okay. So assuming that you did pause or that you were unsure of how to extend what we just tried, Let's look at least the second property here, number 2. So again, with any of these properties, it's good to just start with what's on one side and use the definition and see if we can get what is on the other side. That's really our goal here. So for this first one, this a to the m is just a multiplied by itself m times. And the second one is b multiplied by itself m times. Okay, so again, just as in the last property, our multiplication doesn't actually, or sorry, our parentheses don't actually matter here because multiplication is associative. And I can go ahead and change the order of all of these elements. So I could write this as AB times AB times AB a bunch of times. And in fact, every single A will have a B that it's paired with since there's M of both of the A's and of the B's. So I can just kind of pair them up together by just slowly moving them around. And so each one of these is going to occur M times. And by definition, that means that this is the same thing as A times B to the M. Great. So that's my first 2 properties, or the justification of my first 2 properties of exponents here. If I multiply 2 things that have the same base, then I just go ahead and add the exponents here. If I multiply 2 things that maybe have different bases, but have the same exponent, I can multiply the bases under that exponent. The third property here says that if I have a to some power raised to a power again, I can multiply the exponents. So it's really, I'm going to just flag the difference between number 3 and number 1 is a really important, there are some important differences between 3 and 1, and knowing when to use each one is really important. So here I have the base repeated. So this is a to the m times a to the n. Here on the left, I have a to the m raised to a power again. Okay, and so when I have these 2 things multiplied, my main operation here is multiplication, then I'm going to add the exponents. When I have my last operation here being like another power, raising this to the nth power, then I'm going to multiply those exponents. So it's really good to solidify the distinction between these 2 properties very strongly, because this is where a lot of students will make a mistake that they'll want to combine these 2, combine this by writing this as a to the m times n, but that's not true. This is a to the m plus n and vice versa. So make sure you really, those 2 distinctions really sink in for you. Okay, 2 more rules or properties that we'll discuss for exponents. The fourth one is when we're talking about division. So if I have a to the m divided by a to the n, this is the same thing as a to the m minus n. Okay. And so again, I'll leave thinking about this justification to you. But one thing that this means is that if I have 1 over a to the n, then this is the same thing as saying like a to the 0 over a to the n. So this is a to the 0 minus n is how this rule works. If I divide a to the m by a to the n, I subtract the exponents. And so this is a to the negative n. So what this rule tells me is that these negative exponents are really the same as dividing by that power. Okay, or taking the reciprocal. And likewise, so I can use, I can rewrite this negative exponent into a positive exponent by moving it to the denominator. And likewise, if I was dividing by a to the negative n, I can move that to the top by making it positive. So I can kind of switch if I have a power on the top or the bottom of a fraction, I can switch where it is by just making that power negative or changing the sign of the power. Okay, and then this last property, we've actually already alluded to, it's just the fact that a to the 0 is 1 for all whole numbers not equal to 0. Okay. Okay, so why justifying this property for exponents, that a to the 0 is 1, can be done a few different ways. But I think a nice way to think about it is for a lot of these exponent properties is to look at patterns. So for instance, if I think of, so why is this true? If I'm thinking again about a being non-zero, so let's think about maybe 2 cubed, 2 squared, 2 to the first power. And then what I really want to know about is, say, something like 2 to the 0 power. Well, 2 cubed, that's just 8, right? 2 times 2 times 2. 2 squared, that's 4. 2 to the 1, that is 2. And what I notice is that as I go down, I'm really just dividing by 2 each time. So I go down this list. And of course, I can start off higher with 2 to the 4th or 2 to the 5th kind of up here. And I'd notice the same pattern. And so what I expect, or following this pattern, is that if I divide by 2, again, this should be 1. Okay. Great. And I can do this for any non-zero whole number. I could do this same kind of pattern, looking at any base, any non-zero base, and looking at that pattern there. And I should expect that if I keep dividing, I'm going to get 1 for a to the 0. Okay, so notice we do exclude 0 here. So you might want to know what happens with 0 to the 0. Well, on one hand, if I kind of do a similar process, let's look at 0 cubed, 0 squared, 0 to the 1 power, and 0 to the 0 power. So let's look at the same base and raise it to different powers going towards 0. So 0 cubed is 0 times 0 times 0, that's 0. 0 squared is 0. 0 to the 1 is 0. So here, if I follow the pattern, I expect this to equal 0, right? However, if I follow another pattern, if I instead look at what happens when I look at 3 to the 0, 2 to the 0, 1 to the 0, and so on. So looking at this pattern, I just said that 3 to the 0 is 0, 2 to the 0 is, 3 to the 0 is 1, 2 to the 0 is also 1, 1 to the 0 is 1. So following this pattern, I would expect 0 to the 0 to be equal to 1. And these things are not the same, right? And so we can't have 0 to the 0 being both 1 and 0, and that's why 0 to the 0 is undefined. Just like division by 0 was undefined when we talked about division. Okay, so now that we've talked about all these different operations, we've talked about multiplication, division, addition, subtraction, and exponents, we'll finish off by just recalling the order of operations. And there's, of course, a lot of different ways to remember the order of operations. The way that I was always taught to remember it was PEMDAS, or please excuse my dear Aunt Sally. So this tells me I would use parentheses first. Oops, sorry. And then exponents, multiplication, division, addition, and lastly, subtraction. And I should note that these last, so these two, multiplication and division, and these two, addition and subtraction, actually come at interchangeable. They're like really one step. They're at the same order, just reading from left to right. So I just do whichever is of these two is first from left to right, and same thing with these two. And there's nothing special about this particular order of operations. This is honestly just a convention. It's just a convention so that there's not confusion about what you're being asked to compute. So this is just a tool for communication, just like anything else. Like the fact that we read from left to right is just a convention in English, but in other languages, you read from right to, like Arabic, you read from right to left. So there's nothing right or wrong about using this. This is just how we communicate, and we are telling you what this computation is, what this computation means. Okay, so practicing following these order of operations. Okay, so in this expression here, if I wanted to compute this, what the order of operations says is I first do what is in parentheses. And so I'm going to first perform this operation in parentheses. 1 plus 2 is 3. So this is 5 cubed minus 4 times 3 squared. And then I perform my exponents. So 5 cubed, I think that is 5 times 5 is 25, times 5 again is 125. And then 3 squared is 9. So performing both of those exponents. Okay, my next step is either multiplication or any multiplication or division I have. So here I'm going to do this multiplication. So 4 times 9, that's just 36. And last but not least, I'll do my last operation here, which is subtraction. Okay. So that is how this order of operation works. Okay, for another example, for each of the following, so this is an example similar to, I think, something that shows up in your homework. This is number 14 on page 122 of your text. I'm just going to do part A here. So for this example, we want to show that the expression is not equal to the numerical value. So there's an expression here and a numerical value, and I want to show that they're not equal. And then I'm going to insert parentheses in the expression so that it will be equal to the numerical value. So let's go ahead and for part A here, let's go ahead and look at this expression. Okay, so again, there are no parentheses in this example. So we are first going to do our exponents. So I'm going to, this squared, since there's no parentheses here, is just being applied to the 3. So this 3 squared is 9. My next step is multiplication or division. And I have multiplication here. So this is 2 times 9 is 18. And then my last step would be to subtract that 4. So this gives me 14, not 10, which is what the other value was. Okay, so this was step one. We showed that if I just compute this without any parentheses added in, this is 10. And now I want to insert some parentheses so that the value of this expression with parentheses added in is actually 10. Okay, so for something like this, you might need to try testing around with a couple different options here. But I think what works is, let's see, is if I put parentheses around the 3 squared and the 4 here. Okay, in that case, so I still do the 3 squared first. I still do my exponents first. Well, I guess I do what's in parentheses first. And to do what's in parentheses first, I'm going to do this exponent in the parentheses before that. So this is 2 times 9 minus 4. And now in my parentheses, I will do this subtraction. 9 minus 4 is 5. And 2 times 5 is 10, which is exactly the value that they wanted us to get. So this is where I put my parentheses. So looking for in part 2. Okay, great. A couple other examples that I thought we could end off with just to solidify some of the concepts we learned at the end here. This question number 4 here, this is on page 121. It asks us about the transitivity property. And so remember, this is the property that held for the inequality. Let's find it here. It is this property. And so we said if A is less than B and B is less than C, then A is less than C. And when we were talking about this property, we said it does also hold for equality. So if A is equal to B and B is equal to C, then C has to be equal to A as well. However, so we already said this was yes. The question also asks about part B here, asks what happens with inequality, if inequality is transitive, not equal to. So it is asking, so number 4B is asking if A is not equal to B and B is not equal to C, is A also not equal to C? Can we conclude that A is not equal to C? So maybe think about this one for a moment. And it feels like this should also be transitive, that we should be able to say that A is not equal to C. But I don't think that is necessarily true. So for instance, what if we chose A to be 2 and B to be 0? So then 2 is not equal to 0. And then B is 0 again. What if we chose C to be 2 as well? This is still true, right? 2 is not equal to 0 and 0 is not equal to 2. But 2 is equal to 2, right? So this is my A, this is my C. But this does hold. So inequality is not transitive. Okay, so another example I thought we'd just touch on, just so we knew what these directions we're getting at here. So some of them are a little bit ambiguous even for me. And so in that case, I will definitely make sure that, hopefully the grading is sufficiently generous, because I don't think these directions are quite clear enough on exactly one correct answer. In other words, there are many correct answers. They just tell you to rewrite the following expression in a simpler form. So for part F, and I'm supposing they want you to do it using exponents. So the first thing I might do is kind of rearrange things so that my 5s are together and my 6s are together. Since this is all being multiplied, I can do that, right? Multiplication is commutative. Okay, so this is 5 times 5 times 5 and 6 times 6 times 6. There are 3 5s and 3 6s. So writing this in terms of exponents, this is 5 cubed times 6 cubed. And this is one way I would think would be a fine way to leave your answer. So I would accept this as an answer. But maybe they wanted us to simplify a little bit further. So you might notice that, okay, these bases are not the same, but the exponents are the same. And so I can go ahead and use property number 2. I have the same exponent. And so I combine the bases and raise them to that same exponent. Okay, so this is 5 times 6 cubed, or 30 cubed. So I think either form would be roughly what they were looking for in this answer. Yeah, because they said to do it using exponents. So I imagine what they're looking for is 30 cubed, but it's a little ambiguous. Okay. So this one I might write as like x squared times y to the 4th. And I think that's probably about as simple as we could get it. There's maybe some other forms that are roughly as simple. Okay, so number 6 here, we can simplify by, so I just want to comment, they actually just want us to multiply these things out. So 5 times 5 is 25, 4 times 4 times 4 is 64, and then order them. Okay, number 7, I'll look at just A here for a moment. So this is having us basically do the opposite of what we did for number 5. They want us to write the exponents in the expanded form. So for A here, this is 3x squared y to the 5th times z. So they just want us to expand out each of these exponents. This is 3, and then x squared is 2 x's multiplied together. Y to the 5th is 5 y's multiplied together. And then there's just 1 z. And I think that's all they're really looking for, is this type of expanded form. Great. And of course, we could do something similar with B and C. The important thing to note here with B, the difference between B and C, is when there are parentheses, it means we're cubing everything in this parentheses. When there are not, we're just cubing the number like closest to that 3. So in this expression, only the 5 is being cubed. In this expression, it's that whole 7 times 5 that's being cubed. So there should just be 1 7 here times 3 5s, and then there should be 3 7s and 3 5s in part C. Okay, number 8, might do a couple different ones. Actually, I've just circled one, but let me think here. There are a few. Okay, few ways we could do some of these. So maybe let's look at B first. Let's see, this is 3 to the 12 divided by 3 squared. Okay, so here this is using that division property, and we have the same base. So what that means is we can subtract the exponents. So 3 to the 12 divided by 3 squared is equal to 3 to the 12 minus 2, which is 3 to the 10. So this is using, was that rule 4? I think it was. I won't number it because I don't want to be wrong, but I think it was the 4th one that I had circled there. Let's see here. Looking at C here, this is 2 to the 7th times 2, or times 5 to the 7th. So notice my bases are different, but my exponents are the same this time. And so I think this was our second rule or property, which said if my bases are different, but my exponents are the same, I can combine the bases to this new exponent. So this is 2 times 5 to the 7th, which is 10 to the 7th. Okay, let's look at E and F. Just for good measure here. So E wants us to simplify something in this form. So now here I have to be careful. I do have the division, but unlike for B, where my bases were the same, my bases are not the same here. I have 25 as one of them and 5 as the other. So when something like this happens, where my bases are not the same and my exponents are not the same, what I want to try to do is rewrite the base if I can. So there's a couple different ways that I can do this. I could write 25 as 5 squared in parentheses, or I could write this whole 5 squared as 25. So in the first option, this looks like 5 squared cubed divided by 5 squared. Okay, so this is 5 squared cubed divided by 5 squared. Now I need to be careful before I try to use this division thing. I should really clean up what's happening with these exponents, right? I don't want to end up subtracting 3 and 2. I should really combine these first. So this is, remember, this rule is something to a power again. So that's where I multiply these two exponents. So this is 5 to the 6th divided by 5 squared, not 5 to the 5th. Okay, so remember this distinction, I add the two exponents when it's like the base repeated, but I multiply the two exponents if it's something raised to a power and then raised to a power again. So this is rule 3. Okay, now I can finally use that division rule, which says this is 5 to the 6th minus 2, which is 5 to the 4th. Okay. As I said, you could have also instead of rewriting 25 as 5 squared, you could have rewritten this second piece, this divisor, I think it is, as 25, right? 5 squared really just is 25. And now these have the same base. The exponent here is, of course, just 1. So if I subtract their exponents, this is 25 to the 3 minus 1, or 25 squared. And these two values are totally the same. And you can kind of see this. This is 5 squared squared, since 2 times 2 is 4, which is 25 squared. Okay, so either way of writing this answer, I think, is totally fine. And either method is totally fine. In fact, you might have another series of steps that you would get to either one of these answers. And I think that's fine. The directions are slightly ambiguous. Okay, so let's look at F. Just for good measure, getting practice with these, I find the exponents can be really one of the tricky parts for a lot of people. Okay, so this was 9 squared, 12 cubed times 2. Okay, this was part F of that problem number 8. Okay, so I would do a similar thing that I did here, where I rewrote this 25 as 5 squared. So I really tried to think of like um, the smallest factorization or the prime factorization of 25. So I'm going to do the same thing here with 9 and with 12. I'm going to try to rewrite those as products. So 9, that's really 3 squared. And 12, that's really 3 times 4 or 3 times 2 squared. If you want to do that in 2 steps, that's totally fine. And then, of course, I'm just going to leave that 2 on the end. So this is really my 9, and then this is really my 12, since this is 3 times 4. Okay, so when I have something raised to a power and then raised to a power again, I multiply those two exponents. That's how that rule works, right? So let's see here. This looks like 3 squared is 3 to the 4th. And while exponents don't distribute over addition, they do distribute over multiplication. In fact, that's really what this rule says is if we use rule 2 kind of backwards, it says if I have some product raised to a power, it's really a to the m times b to the m. So I can distribute exponents only over multiplication. So this says like exponents distribute over multiplication, not over addition, not over subtraction, is really what that rule says. So let's go ahead and distribute this exponent over this multiplication then. This is 3 cubed, and this becomes 2 squared cubed. So that's using that, I think, second rule. All right. Now I have a few different steps I can do in the next iteration here. You might notice these both have the same base, so I can combine their exponents by adding, right? So here I have a power to a power, so I multiply, but here I have these two things being multiplied, so I add the exponents. So that's 4 plus 3, that's 7. And then in this piece, again, I have a power to a power, so I multiply the exponents. So really emphasizing the difference. This is two things being multiplied with the same base, so I add the exponents to get 7. Here I have a power to a power, right? They actually look quite different. So you have to, so make sure you kind of really sink in your mind, but you do something very similar, so you have to be careful, right? Here we're multiplying, oops. In this case, we're multiplying the exponents. In this case, we're adding the exponents. Okay, so 2 times 3, that is 6. Great. Okay, so again, there's an invisible 1 sitting up here with this 2. So this is 3 to the 7th times 2 to the 7th. And last but not least, I have the same exponent up here. So if I want to, I might want to combine these bases to be 3 times 2 to the 7th or 6 to the 7th. Great. Okay, so that finishes off that example. I thought I would end here. So notice, this is one example 10. Can't remember if this shows up in a different problem or not, but this is one that I'd really recommend for a problem to present in the discussion, in a video form. Number 10 here, again, this is page 121. And I'll talk through at least parts A and C of number 11 here. So number 11. Okay. Let's see here. So let's see, a is 3 to the 7th times 3 to the x is equal to 3 to the 13th. And I'll just write this one down. 3 to the x times 2 to the x. 6. Okay, great. Oops, 6 to the x. Okay. Okay, so for these problems, let's just look back at the directions real quick. What we want to do is find the value of x that makes this equation true. Okay. So what value of x makes this true? Well, remember when I have two exponents, I have the same base here, I add the exponents. So I need for 7 plus x to equal 13. So on the left-hand side, this is 3 to the 7 plus x. So 7 plus x equals 13 is what I'm really trying to solve. And so that means x has to equal 6. Okay, so if I put in 6 for x here, that would give me 3 to the 13th. Okay, so for this one, we want to find the value of x that makes this equation true. So I want to think about, again, kind of simplifying one of the sides and seeing what makes it true. So here I have the opposite rule, right? Here I had the same base, so I can add the exponents. But here I have different bases with the same exponent. That means I multiply these bases with the same exponent. And really this left-hand side, that's just 6 to the x, right? So this says 6 to the x is equal to 6 to the x. Right? This is 6 to the x and this is 6 to the x. When is that true? Well, that's actually true for all x. So this is actually number 11 was, or sorry, part A was true for only one particular x value, x equals 6. But part C was true for any x value we choose. If I put 1 in here, this is true. If I put 2 here, it's true. If I put 1,000,000 in there, it's still true. Great. I just wanted to point out a couple more problems that I recommend looking at and maybe writing out for the discussion. I think there are a lot of good problems at the end of this chapter. So number 22 here in particular, I think would be a nice thing to write up for the discussion. This is on page 123. Here we have, this is actually, I think, that fourth property we talked about with division. So this would be a nice one to write up for the discussion post. Number 29 here is a kind of a different flavor, but of a similar type of problem. So here we're looking at a rule, but this is one that your student has kind of contrived or written down themselves. And you want to say if this student is correct or incorrect, if this is a rule or not a rule, and explain why. So you'll compare this rule to our list and you'll probably notice it's not a rule on our list. But you want to do a step further and ask yourself, but is it a true statement? Why or why not? Okay, so is it correct or is it incorrect? So it could be not a rule on our list and it could still be a totally correct thing. But it also might not be. And then I think number 30 is actually basically the same version or very different or a similar version to number 10 here that I mentioned above. Okay, well, with that, we'll end here and good luck with your homework and I will see you next time.